In section 2.3, we're going to be talking about measures of central tendency. This section of notes has about 6 pages, so I'm going to try and get it done in one video, but we'll see how that goes. So let's talk about what is a measure of central tendency. A measure of central tendency is a value that represents a typical or central entry of a data set. Some examples of measures of central tendency. You are going to be familiar with a few of them. Mean is a measure of central tendency, as is median, mode, and midrange. Now, midrange is one that's not very commonly used. It's only used in circumstances where the other ones are not valid, but we will talk about it. So let's just as a refresher go over the terms statistic and parameter and get a little bit more detail. Remember that a statistic is a measure or characteristic that is obtained from a sample. Statistics are going to use Roman symbols. Roman symbols are the letters that we're used to using, but they also have other like accents that go along with them. So, for example, with a statistic, this symbol right here is what we use for the mean, and it is read as X bar. So it's an X with a bar over it, and that stands for a sample mean. Parameters, by contrast, are measure or characteristic obtained using all data values from a specific population. So statistics are going to come from a sample, but parameters are measures or characteristics obtained using all data values from a specific population. Now, parameters are going to use Greek symbols. So these will not be as familiar to you, and you'll definitely need to pay attention to the difference between which symbol is used. So the symbol for mean when you're working with population data or a parameter is this symbol right here. It's kind of a U with a longer left tail and a little curly right tail. This is mean, and it is read mu with a long U, mu. The rounding rule when you're working with statistics and parameters, this is going to be a general rounding rule that we will use for any situation unless it is specified to follow a different protocol. So the round off rule is that you do not round until the last calculation. So you'll want to keep your calculator handy, make sure all of the decimal places stay in your calculator as you're doing your computations until the very last one. And then here's the rule that you will round to 1 decimal place further than the data. Now, this is a thing we might want to highlight or somehow mark so that you remember where it's at. The round off rule, 1 decimal place farther than the data. Not real sure if you can tell that that's highlighted. Let me put a different color there. Maybe it'll pop a little bit. Anyways, I highlighted it. Okay, let's go on to figuring out how to calculate these measures of central tendency. So we'll start with the one that you're probably the most familiar with, which is the mean. The mean is equal to the sum of the data values divided by the total number of values. So I'm going to give you a formula, and then I'm going to tell you like what all the different symbols mean in it. So we have two different formulas depending on if we're working with sample data or population data. And the reason for that is because we have different symbols if we're using sample data or population data. Remember, the symbol for the sample mean was X bar. And the way that we write this formula using mathematical symbols is to say that the mean is equal to the sum of the data values divided by the number of data values. So the symbols we've used here, I'm not sure if we've seen this one already this semester, but this means to add up all. It's the symbol for summation. It's a capital sigma. And so what it really means is add up all or find the sum. So what we're adding up is the x's. So the x stands for an individual data entry. So this means add up all of the individual data values and then divide by n. We've seen n before. N is the sample size. And that will be consistent throughout the semester. When we use the letter n, we're referring to sample size. Now for a population, remember we use the Greek letter mu. So mu is equal to, again, we're going to add up all the data values, but this time it's not a sample size, it's a population size. So we actually use a capital letter N to represent the population size. Okay. Next up, we have median. The symbol for median is capital M, capital D. And what it is the midpoint of a data array. Now, you may not know what a data array is, so we'll talk about that for a moment. A data array is data that is arranged in order. So in order for us to be able to find a median, we first need to make sure that our data is in order from smallest to largest. And then we're going to just kind of count to the middle. Well, if there's an odd number of data values, then there will be a middle value. If there's an even number of data values, then there won't be a middle number. So we need a rule to deal with that. So if there is an even number of data values, then the median will actually be the mean of the two central values. You're probably familiar with those rules. Moving on to mode. Now, mode is a pretty simple concept. It's the value that occurs most often in a data set. However, there are some guidelines for, what happens if there's, no data value that occurs more than once, or if there's a tie or something like that. So if no data value occurs more than once, then there is no mode. If more than one data value occurs with the same greatest frequency, in other words, there's a tie between 2 or 3 or more values, then we say that the data set has 2 modes, or it could be called bimodal, or there's more than 2 modes, and then we call that multimodal. So we have a tie between data values. There can be 2 modes, in which case we would call the data set bimodal, or more than 2 modes, in which we would call the data set multimodal. The mode is the only measure of central tendency that can be used with categorical data, or data that's at the nominal level. So if you're working with qualitative data rather than quantitative data, then the only measure of central tendency that is valid is going to be the mode. Or if we're working with like Jersey numbers or something like that. If you have grouped data, which we have not yet looked at a grouped frequency distribution. So I'll talk about it now, but it may not mean as much until we get to a grouped frequency distribution. Modal class is for grouped data. So that's when we're looking at like a histogram that's showing like a range of values. So for group data, you can have a modal class, and what that modal class is the class that has the highest frequency. I guess we have done grouped frequency distributions. Okay, let's talk about one other vocabulary word before we move on to an example, and that is going to be an outlier. Now, we will have a more technical definition of outliers later on when we get to work with standard deviation, but for now, just know that outliers are extremely high or extremely low data values. Now, when you're working with measures of central tendency, outliers have a very strong effect on the mean because we're adding up all the numbers and then dividing by the total number of values. So if you have an outlier in your data set, you should not use the mean as your chosen measure of central tendency because it won't describe the overall data very well. When you have an outlier, you should choose the median as the measure of central tendency to best represent the data. Because it doesn't matter how big the highest value is and how small the lowest value is, the middle is still the middle. Sometimes outliers are actually valid data. Like there's just one piece of data there's one measure that's really, really significantly higher or lower than the rest. But other times, it may be an error in data recording. So how does that happen? Let's say I'm going along and I'm reading data and I see 9.4, but I write 94 because I'm in a hurry, or the decimal is faint and I can't really see it. So, mistakes happen. So we have to be aware of outliers. And when we have outliers, you have to know that any conclusions that are drawn about that data set may be flawed. So there are guidelines about when outliers are present, what to do when you're drawing conclusions. Like sometimes outliers can be omitted, sometimes they cannot. And there are definite mathematical ways to identify an outlier. And we'll get to that later. Okay, we're going to look at an example where we compare the mean, median, and mode. So find this example, comparing the mean, median, and mode. And we're going to get to practice finding all of these measures. So you might want a calculator. I'll get mine out. So we are going to find the mean, median, and mode of the sample ages. So they're telling us it's a sample of students in a class shown at the left. Which measure of central tendency best describes a typical entry of this data set? Are there any outliers? So we're going to first figure out the mean, median, and mode. And then we'll talk about midrange. I don't know why I didn't mention it before, but we'll get to that in a minute. So the mean, since it's a sample, the symbol we use for mean is X bar. And remember that X bar is the sum of the data values divided by the sample size. So the first thing we need to do is add up all the data values. So that just takes a little bit of time and your calculator and being careful. Ooh, that 65 is weird. When I add those all up, I get 475. And I've got 3, 6, 9, 12, 15, 18, 19, 20. 20 data values. So I'm going to do 475 divided by 20. And that gives me 23.75. Now, remember the round off rule is that we are going to wait till the very last step, and then we're going to go 1 decimal point further than the data value. So it'll be 23.8 will be our mean. Then our median, remember the median, we put the data values in order, and then we choose the middle data value. Well, since we have a even number of data values, the median is going to have to be the average of the two middle values. So knowing that we have 20, I can kind of count in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my two middle numbers are 21 and 22. So I'll do 21 plus 22 divided by 2, which is 21.5. So there's my median. And then the mode is the number that occurs most frequently. So I've got 1, 2, 3, 4, 5, 6 that are 20. 1, 2, 3, 4 that are 21. 3 that are 22. 1, 2, 3, 4 that are 23. So my mode is going to be 20 because 20 occurs the most frequently. So then we need to decide which one best describes a typical entry, and do we have any outliers? So looking at the data values here, I'm like almost like everyone is under the age of 25 except for this 65-year-old person. So I would say that we might possibly have an outlier, and it's the number that's 65. So remember what we talked about in terms of the measures of central tendency, that we should not use the mean because of that outlier. So I would say not to use the mean because it's too high due to the outlier. Now, if we look at using the median, remember what we said about the median? The median is resistant to the outlier. And we said that in the case of an outlier, we should use the median. So this would be the one I would choose to use, 21.5. And then the mode might be an okay one, but in this case, what's true about the mode? If you look at all the data values, the mode being 20 would not be a good representation of the class because the mode happens to be the lowest data value. So it's probably not a good representation of the class age. So what I'm going to have us do is we are going to figure out the mean, median, and mode if we take out the outlier. So we are going to remove the outlier and recalculate. So our mean will now be x bar equals, we've got to take the 65 off. So 475, take off the 65. It gives us 410. And now we don't have 20 data values, we have 19 data values. Divide by 19 acres. 21.57894,737. And it probably goes on from there. But remember that we're going to round. Our round off rule is we go one decimal place further than the data. So that is 21.6. The median, if I take off the 65, then I have an odd number of values. And if I count in to the middle, that's going to put me at 21. So my median will be 21. And the mode is actually going to be unchanged at 20. So what you can see here is that the presence of that outlier caused our mean to be about 2 years higher than it was without the outlier. The median was only half of a year different, and the mode was unchanged. So that's the reason why we say to use the median when you have an outlier present, because the mean is affected, has a strong pull with a high or low data value. Okay, now I'm going to talk to you about midrange, and then we're going to calculate midrange. So midrange is the measure of central tendency that I have not described to you yet. And it uses the letters MR. And what it is that we're going to take the highest data value plus the lowest data value, and we're going to divide it by 2. Now, it's not a super great measure. We'll look and see with our example, we'll use the outlier. And then we will refigure it without the outlier. This is the same example we were just working on. So with the outlier present, our mid-range would be the highest data value, which was 65, plus the lowest data value, which was 20. Divide that by 2, makes 85 divided by 2, so 42.5. Without the outlier, the mid-range would be, let's see, take the outlier off. Now our highest data value is 24, and our lowest is still 20. So 24 plus 20 divided by 2 gives us a mid-range of 22 years. So the mid-range is also going to be strongly affected by the presence of an outlier, since it's using the highest and the lowest data value. So let's talk about finding a weighted mean. Here in a minute, we're going to be using the example that's finding a weighted mean, but first I want to tell you about weighted mean. Now, weighted mean is commonly used like for figuring out your grade in a class or for figuring out your GPA. In a weighted mean, it's going to use the same formula or the same symbol, X bar. And what a weighted mean is the mean of a data set whose entries have varying weights. So one category doesn't count the same as another category. Like, for example, if you have a 3 credit hour class, that counts differently than a 6 credit hour class. So it's commonly used in GPA calculations. So in GPA, then the weight of the class is actually the number of credit hours. We'll do an example with that in a moment. So to find weighted mean, there's a formula. It's the sum of X times W. So we've seen X. X is the data values. W we haven't seen before. It is the weight of the entry. And then it's divided by the sum of the weights. So we'll practice on this one and then we'll do a GPA example. You are taking a class in which your grade is determined from 5 sources. 50% from your test mean, 15% from your midterm, 20% from your final exam, 10% from computer lab work, 5% from homework. Your scores are 86, 96, all these grades. What is the weighted mean of your scores? So what we're going to do is we're going to create ourselves a little table where we're going to list the category. We're going to list the weight. We're going to list the value of the data, which is X. And we're going to then figure out, because the formula uses X times W, so we'll figure out X times W. So our categories are test, which was 50%. So I'm going to use 0.5 for my weight. Midterm, which was 15%, so I'll use 0.15. Final exam, which was 20%, so 0.2. Computer lab work, which was 10%, so 0.1. And homework, which was 5%, so 0.05. The value of the data is going to be what I actually earned in each category. So my test mean was 86, midterm 96, final exam 82, computer lab 98, homework 100. In the formula, it tells us to add up X times W, which means first we do X times W and then we add up all those results. And we're dividing by adding up all the W's. So we can easily add up all the W's here in this column. just by adding all of these values here. So we got 0.5 plus 0.15 plus 0.2 plus 0.1 plus 0.05. And that equals 1. Then we're going to fill in this column, x times w. Once we have that filled in, then we'll add up those values, and that will give us the sum of x times w. So we're going to do 0.5 times 86, which is 43. 0.15 times 96, 14.4. 0.2 times 82, 16.4. 0.1 times 98, 9.8, and 0.05 times 100 is 5. And we're going to add up this column. Oops, I have a little mistake there. And I get 88.6. So for my weighted mean, the weighted mean, x bar, is the sum of x times w divided by the sum of w. The sum of x times w was 88.6. The sum of w was 1. So my weighted mean is 88.6, which means that in the class, I will get an 88.6%. Now, it tells me that the minimum average for an A is 90. Did I get an A? No, I did not get an A. Sadly, I got a B. Even though my midterm, my labs, and my homework were all solid A's. Okay, now we have to write out an example. So I am going to pause it, write it out, and then once you see it written out, you can pause it and write it out. Okay, here is the example we are going to do. If you have an A in your 3 credit hour English class, a B in your 5 credit hour math class, and a D in your 1 credit hour PE class, what is your semester GPA? So this is going to need to be a weighted mean problem because our classes are worth varying amounts. So we will write out our categories, our weights, our data values, and then x times w. So for the categories, we'll just use the names of the classes. So we have English, math, and PE. We don't have a very full schedule. Then the weights are going to be how many credit hours they are. So for English, the weight is 3. For math, it's 5. And for PE, it's 1. The data value is going to be what our letter grade was. So letter grades are worth different amounts of points. An A is 4 points, a B is 3 points, C is 2 points, a D is 1 point, and if you're failing a class, it's 0 points. So we had an A in English, so that's 4 points, a B in math, so that's 3, and a D in PE, which is 1. And then we'll take the weight times the data value. So 3 times 4, that's 12. 5 times 3, 15. And 1 times 1 is 1. Remember, for our mean, weighted mean, x bar would equal the sum of x times w divided by the sum of w. So we'll add up our weights. Sum of w is 9. Now that happens to be the number of credit hours that you're taking in the semester. So we're going to be dividing by 9. And then we're going to add up this column, sum of x times w. So 12 and 15 is 27 plus 1 is 28. So that's how many credit points you earned. But to get your GPA, we have to take the 28 divided by 9. And we're going to get for our GPA is 3.1. Now, by traditional rounding rules, we would just put 3.1. But in a GPA, they go out 2 decimal places. So our GPA would be 3.11. All right, next up, we are going to be finding a mean for a frequency distribution. This is where we're going to be using classes instead of having raw data. So, mean for a frequency distribution. We have an example that goes along with this. So if you have this one handy, we'll be using it momentarily. So first I'm going to give you the instructions. So for a frequency distribution. So frequency distributions are like these tables that have classes in one column, like 30 to 35, and then 36 to 41, 42 to 47, and then we have frequency in the next column. So like 7, 12, 3, whatever. This is just an example of what a frequency distribution looks like. So what's happening here is we don't have the raw data. So we can't actually add up all the data values and figure out the mean that way. So when we're figuring out the mean for a frequency distribution, we have to have a different strategy since we can't add up our data values. So here's going to be our steps. Is the first thing we're going to do once we have a frequency distribution is we will add a column to the right-hand side for the midpoints of each class. Now, we did talk about how to find the midpoint at one point. The midpoint is x sub m. And to find the midpoint, we are going to take the upper data value plus the lower data value and then divide by 2. So it's the upper class plus the lower class. The upper endpoint plus the lower endpoint, or class limit, divide by 2. Then you're going to make a column for x sub m times f. Remember, f is frequency. At the bottom of that column, you're going to find the sum of x sub m times frequency. Then we have the formula for mean. It's going to be 2 formulas. One will be x bar. That's if we're working with a sample. So we find the sum of x sub m times frequency, and we're going to divide that by n, which is the sample size. Or if we have population data, it's going to be mu equals that same sum of x sub m times frequency, but now our sample size is not a sample size, it's a population size, so it's that capital N for population size. So we'll work through this example. I'm going to rewrite my data table because I don't feel like I have enough room over here. I could have planned that out a little bit better, but it's too late for that. So I'm going to make a column for classes and then a column for frequency. And then remember it said I need to add a column for midpoint, so x sub m, and then a column for x sub m times frequency. So for my classes, if my class midpoint was 12.5, and then my next class midpoint is 24.5, then what that tells me is 24.5 5 minus 12.5. It tells me that my class width is 12. So in order to have 12.5 as my class midpoint, then my classes would need to be, 12 wide. So I'm going to have, this class will be from 7 to 18. And the frequency is 6. Now they did give me my class midpoint, but you can see if they didn't give me my class midpoint and all I had was my class, then I would take 7 plus 18, which is 25, divide by 2, which gives me a midpoint of 12.5. So going along with the class width of 12, my next class would start at 19, and then plus 12. My next class starts at 31, plus 12 is 43, plus 12 is 55, plus 12 is 67, plus 12 is 79. And then my upper class limits, I add 12 each time again. So 30, 42, 54, 66, 78, 90. Okay. Then my frequencies were given. So I'm just copying those out of my table. And then I want to figure out for my sample size, well, is this a sample or a population? Use the frequency distribution at the left to approximate the mean number of minutes from a sample of internet subscribers. The number of minutes they spent online during their most recent session. So to figure out my sample size, that's adding up all my frequencies. So my sample size will be, when I add these up, so 50. Then I'm going to continue finding my midpoints. Actually, they were given, so I'll just write them down. Notice that my midpoints are also 12 apart from each other. And then I need to find this column, the midpoint times the frequency. So I'm just going to multiply these two numbers together. So 6 times 12.5, 75. 10 times 24.5 is 245. 13 times 36.5, 474.5. 8 times 48.5, 388. 5 times 60.5, 302.5. 6 times 72.5 is 435. And 2 times 84.5, 169. Now, in that formula, I need to have the sum of this column. So I'll be adding up those numbers. 75. That is 2,089. So then my formula is that X bar equals the sum of XM times F divided by N. So X bar will be 2,089 divided by 50, which is 41.78. So since I don't really know what my data values were originally, but since it's the number of minutes, I'm going to guess that it was whole numbers. So we'll go 1 decimal point further than that data. And we'll say that the mean number of minutes that this sample of internet subscribers spent online during their most recent session would be 41.8 minutes for X bar. What's next? Next thing we're going to talk about is distribution shapes. Distribution shapes. There are 4 basic types we're going to talk about. One is called a uniform. Mostly they call it uniform, but they can call it a rectangular distribution. Okay, if I could spell, that would be good. Rectangular distribution. So what we're talking about is like the distribution of, say, a histogram or a frequency distribution. In a uniform distribution, all entries or classes have equal or approximately equal, approximately the same frequencies. So if we have, of course, on all of our frequency distributions, the vertical bar is frequency and the horizontal bar is like the classes or the entries, the entry values. So what we've got going on in a uniform distribution is that all of our classes or all of our data values are equal or approximately equal in frequency. So it kind of makes this rectangular looking shape, which is where it gets its name of a rectangular distribution. And in a uniform distribution, since the data values are all essentially the same, then what happens is that here in the center is going to be the mean as well as the median. So the mean and the median are going to be the same, and they will be right in the center of that distribution. Our next one is going to be a symmetric distribution. Oh, I don't know if I said 4 or 5, but there's 5 shapes we're going to talk about. In a symmetric distribution, what is going to happen is that we can draw a vertical line through the middle, and both of the halves are going to be approximately mirror images. So a specific type of symmetric distribution is going to be something we call the normal distribution. So I'm going to draw both of these. I mean, I guess technically they're the same type, but the normal distribution is a special case of symmetrical. So I'm going to write out that description, and then I'm going to draw 2 distributions. So in a symmetric distribution, a vertical line can be drawn through the middle, and both halves are approximately mirror images. Okay, so it might look like this. Where our distribution kind of has this, what we'd call bimodal shape. You can see that if you draw a vertical line through the middle, both halves would be approximately mirror images. In a normal distribution, that's one that just has one mode, and you've probably heard it referred to as a bell curve at some point because it has this nice bell shape. So they look like this, roughly. And again, if I drew a vertical line down the middle, it would be a mirror image. Now, in a normal distribution, right here in the center is where we will find the mean, also the median, and the mode. So in an actual normal distribution, all three of these are equal. Now, in my rectangular or uniform distribution, there would possibly be no mode because they could all be the same frequency. So that's why I did not label mode there. And we have two more types of distributions. We have left skewed and right skewed. Skewed means like not straight, I guess. Cattywampus, if that's a word you know. So left skewed and right skewed. And the direction of skewedness is the tail. So on a left skewed, it's like taking the normal distribution and pulling the tail to the left. And on right skewed, it's like pulling the tail to the right. So left tail is longer. On the right skewed, the right tail is longer. Okay. So we'll talk about how that affects our mean, median, and mode after we draw these. So it's like that distribution, but it's got a longer tail to the left. And then this one is like with a longer tail to the right. So the median for, well, let's label the mode because that's the easiest one. Mode is the highest point because that will be the highest frequency. And then the mean and the median fall differently depending on if it is left skewed or right skewed. So remember when we talked about outliers and we said that the mean is highly influenced by an outlier. So in this case, what we've got is most of our data is up here, but then we have some really, really low values that are going to pull our mean and make it lower. So the mean is going to be over here to the left. And then the median is the middle data value. So actually the median is going to fall in between the mean and the mode. Now, when I have a right tail that is longer, these have really high data values are going to make my mean higher than it should be. So the mean will be off to the right. I'm just approximating where these would be labeled. And then the median would be somewhere in between. So what ends up happening is that the mean falls in the direction of skew from the median. So if it's left skewed, the mean falls to the left of the median. If it's right skewed, the mean falls to the right of the median. And then the mode is always the highest point in those.